Great. Yeah. Thanks, Will. Thank you very much for the kind invitation. Happy to be here. And thanks also everyone else for joining. And yeah, so I will give a little bit of a history of how we developed a community seismic network. And the term community has sort of two meanings here. It's the scientific community that came together. There's a lot of participation from El Salvador, and then also here from University of Memphis and broader speaking. But then we also have community partners, schools, and I will highlight, schools, businesses, and other community partners in El Salvador who are working with us. But yeah, I do want to highlight, so this effort is really maybe one of the largest sort of team efforts that I'm a part of, and all of the students who are in the project are highlighted in blue. And so as I said, so it's obviously us from Memphis here. We're working with the University of El Salvador, mainly the geophysics program in the western parts in Santa Ana. And then we're also working with the Ministry of the Environment and Natural Resources in El Salvador. So as I said, so I do want to highlight just the research team and especially the students. Without their participation, they're very energetic, great group of people to work with, and from both sides. So my students are here from Memphis, Navin Thapa, Sadia Rinti, and recently we have three new students that joined us from El Salvador: Susana, Diego, Figueroa, and Adonai. So they are, they were trained and educated basically in El Salvador and recently started their PhD program here at SERI, at the Earthquake Center. And Josue Estrada is also working with us. He's in El Salvador. Other funding and support. So we recently received funding support from SEG, from the Geoscientists Without Borders, and we have some other partners that are supporting us in various forms. Okay, so this talk, I hope I'll get through all of this. So let's see how we do. But I would like to give you a brief history, how kind of the project kind of unfolded more or less organically and what we're trying to achieve. Then we'll dive a little bit into the science. What is the seismotectonic setting and the eruption history in Western El Salvador? I will explain how we developed the seismic network, and then we'll look at some of our results based on the first catalog that we created. So the project started more from the teaching side. So I had traveled down to El Salvador a couple of times in 2018 and 2022 to give short classes on seismology, on earthquake physics, on induced seismicity. And this is a photograph taken from or after the 2022 course. And so over this time frame, a very close friendship developed with my colleague, Professor Venancio Enriquez, and I hope he's on the call too, but very enjoyable and very nice, the ability to work with him over the years. And anyways, just put in what we did for one of the classes. But Venancio was, before I started anything, he was very interested in research and understanding the volcanic magmatic system better. He witnessed a couple of eruptions. I will show some pictures. And his background is in physics, volcanology. So before I started, he had a team of researchers, student researchers, and another faculty member. And so they were involved in measuring gas emissions, temperature, etc. So then, over the years, we're starting to scheme, look, can we do more than teaching these short courses? Can we develop some more resources that would support their research efforts? And so the idea came, coming from the Earthquake Center, an obvious avenue of support is to develop more seismic capabilities and instrumentation. And so this started, the idea started, in 22, and then we were able to invite a group from El Salvador here to come to SERI the following year in May 2023. And so the idea was to train them in how to use broadband seismometers, how to do basic deployment, and how to do data processing. So Siri actually donated, I want to say 4 or so of a slightly older version CMG 60Ds, the Goebel seismometers. And during that workshop in 2023, we were able to train our El Salvadoran colleagues on these seismometers, right? And so they were here for 2 weeks. We gave them an overview of what the network looks like, what we do, what instruments we use, etc. And then, as said, they received specific training on these instruments, how to deploy. We organized a field trip to New Madrid. Randy Cox here from Earth Science, he was kindly helping out with the field trip and giving us a detailed geological insight. Photo with Mississippi River in the background. And then here, this is now in El Salvador, as said. So they took these instruments with them and put them to good use after the training. The next step then followed already in fall 2023. And the idea was, so the Goebels, since they were a little bit older, didn't have easy telemetry options. If we could develop a real-time seismic network around the volcano. And our key initial goals were education training, and then to use the instruments to start conversations about hazard preparedness. What do you do before, during, after volcanic eruptions, earthquakes, etc. And of course, being a research scientist, and Professor Bonanzi had the same motivation. The other goal, which we didn't quite know if we would get there, is to provide more scientific understanding, right, of the magmatic system, of the plumbing system of the volcano, and if there's potential for detecting magma chambers. So this is how the project started. I was down there in fall 2023. We visited several different schools and started deploying Raspberry Shakes. And one of my students, Naveen Thapa, he came down for, I think, 10 days or so. And he contributed very greatly also to setting up the seismic network. And I will go into the details. What we did here are some of the partners. These are, the community partners, as I highlighted, right? Different types of community partners. But yeah, so we have a number of different schools, educational centers. We're working with 2 hotels. There's one hotel that is very close to the summit, and they were so kind to host one of our Raspberry Shakes, and some additional partners here. Okay, and this is roughly what the setting on the ground looks like, right? This is one of the schools. A lot of them have quite obviously nice facilities, usually open courtyard and then classrooms around. And we went in and started basically, as you can see, duct taping Raspberry Shakes on the floor of different classrooms. And we started conversations about seismic and volcanic hazards. Now, the Raspberry Shake component, you can see all of these stations and access the data through stationview.raspberryshake.org. And the folks from Raspberry Shake were extremely supportive. Their mission, I think, aligned extremely well with our mission, doing seismology and doing a lot of education and training and outreach. So that obviously worked really well too. Now, the last thing I want to mention before we transition here to the more scientific part of the talk, just this fall, the colleagues from the University of El Salvador started organizing a boot camp. What's the boot camp? So, well, this is basically a virtual class every Saturday where I believe it's 10 students from every partner school are trained. There's a total of about 100 or so students who are participating, and they receive education in earth science, volcanology, seismology, as well as hazard preparedness. So I added some nice pictures. This is, of course, not of the virtual classroom, but just to showcase a little bit what different schools look like, right? But yeah, so this effort is completely initiated and led by the University of El Salvador. And I think it's just a great first step to continue or to do more on the outreach and education components. Okay, so we'll transition to the scientific component, and then as said, so I'll show a little bit what the tectonic setting is, then how we started developing the network, and then I will show you the results from our first seismicity catalog. Okay, so just to set the stage, right? So we're working in El Salvador, actually just the western part of the country, and El Salvador is located at the southwestern part of Central America. Tectonic setting is really dominated by the subduction zone here, where the Cocos plate dives underneath the shortest block of the Caribbean plate. Fairly rapid conversion rates, slightly oblique, and so we have repeated evidence of large earthquakes that are out related to the subduction. So these are two recent events from 1982 and from 2001, both normal faulting events within the downgoing slab. So at the same time, we have this motion here on the 4-arc sliver, which supports this strike slip faulting, onshore strike slip faulting. And it turns out that a lot of these onshore earthquakes, which are usually a lot shallower, can be very destructive. And so recent evidence of that destructive nature is, for instance, the 2001 earthquake that affected the capital, San Salvador, and also Santa Tecla, just west of the capital, and caused quite a bit of destruction. One interesting scientific observation to highlight is that there seems to be a close coupling between the subduction zone processes and what's happening onshore. So this is, for instance, seen, right, there's about a 30-day delay between the magnitude 7.7 earthquake in 2001 and then the subsequent onshore right level strike slip in February 2001. But there's also evidence that volcanic eruptions may be advanced or triggered by subduction zone earthquakes, not shown on this map, but 2013 there was a series of subduction zone events, and then also was followed by an eruption of San Miguel volcano in the eastern part of the country. So we'll come back at the end of this talk about some observations about coupling processes that we have in our smaller study area. Okay, so this is just to highlight this again, right? So we got the Middle American Trench, Cocos Plate, and the subduction zone here, and then the shortest block of the Caribbean Plate, and here's El Salvador, which is really traversed by these strike slip faults. So the overall seismic hazard is very significant, as well as the volcanic hazard. And we focused in just on the very western part of the country, and specifically we're interested in the Santa Ana Apaneca volcanic complex. And this is a view from the top, the crater lake of Santa Ana. You can obviously climb up there, and we did this several times. There's a large caldera to the east of our study area, and then this volcanic chain with various peaks, and the most recently active peaks are Santa Ana and Izalco. We'll go into details here in a little bit, but just from the surface topography, there's a lot of evidence of recent activity. There are lava flows. There's a large debris flow that was connected to volcanic flank collapse and traveling almost, I think, all the way to the Pacific Ocean. And yeah, and several conical structures which indicate there was more activity west of Santa Ana in the past. Now, the active volcanoes itself includes not just Santa Ana, which is the highest and largest stratovolcano. There's also Izalco, which is a very interesting feature. I'll talk about this in a minute. And in between is Cerro Verde, which seems to be largely inactive at this particular point in time. And so very picturesque. You can see this from this aerial photograph. Okay. Now let's start with Izalco, and then we'll jump over to Santa Ana. So Izalco has a very long, interesting history of more effusive type eruptions, Strombolian type eruptions, and historically had the name Lighthouse of the Pacific. It's the first clear topographic feature when looking north. If you're an incoming ship on the Pacific, what you see would be Izalco. And at nighttime, obviously, the lava flows would be visible. So this is one or two images between 1954 and 1966, highlighting some new lava flows that happened, and then also a large crater deformation and explosion that changed the top of Izalco very significantly within this 12-year time frame. The last reported eruption is 1966. Obviously I put the question mark, unclear what the future will hold, but it's interesting, right? So you see the sort of this long history of sometimes fairly continuous eruptions, then you have some longer gaps. Unclear if we are in a gap right now or if the eruption or if activity just shifted, let's say, for instance, north to Santa Ana. Okay, and this is from a study that tracked the surface temperature evolution of fumaroles towards the top of Izalco, and we see this longer-term decrease in temperature over these 4 or 5 years, and again the eruption, basically, the somewhat continuous eruption stopped in 1966, and then we see a more rapid decline in the temperature. Okay, so Santa Ana, a very different type of volcanic activity and a lot more phreatic and phreato-magmatic type eruption history, and the most recent and most dramatically 2005. And the ash plume of the 2005 eruption was about 15 kilometers high. There were significant blast effects. Here's another photographic image that would be from the southwest, seeing the even more developed ash plume. The eruption itself obviously caused a lot of damage, but subsequently there was a large tropical storm, I believe Tropical Storm Stan, that triggered a lot of lahars that traveled east towards Lago Coatepeque and destroyed more of the coffee plantations and other agricultural installations around the volcano. So that's, and then there was a smaller eruption that was actually captured by my colleagues from the University of El Salvador. They were up at the summit when this eruption happened and basically had to, as far as I understand, had to run for their lives. But it turned out to be not as large. But this is what the 2007 eruption looked like. Okay. So the 2005 eruption is indeed very interesting. There was a short period seismometer installed close to the summit, and the eruption was preceded by a long period of precursory signals, and included different types, right? So one is the seismic, so there was an increase in long period events. So this is already starting 12 months, more than 12 months earlier. And you can see the LP, the green one, increasing, then decreasing a little bit before basically a final increase, and then the over the course of the eruption unfolding right at the top at the crater lake. And then we have the overall amplitude of the seismic signals, a slight increase in SO2 flux right here in magenta, and sort of also a modest initial increase in the lake temperature, and then a fairly high jump in terms of heating up the crater lake over the course of the eruption. So that's kind of interesting. It seemed to indicate that Santa Ana may produce very elaborate precursory signals that can be characterized and analyzed and used and can be used to understand better the processes leading up to eruptions, right? So based on that, right? So that was obviously part of the motivation. Can we improve the situation in terms of what's available in terms of seismic instruments? And then the key idea was obviously to make also everything available for research, both for us here, for the colleagues in El Salvador, and for anyone else. Now, okay, let's jump into the network development and deployment. As I highlighted earlier, right, we had the three key goals: education, train students, support the curriculum at the university. Wanted to use this as tools for outreach and preparedness. Since we were working with schools, it's sort of an easy, natural way to start conversations about their hazard, and a lot of the schools are between 5 to 20 kilometers. Santa Ana itself and the university are just about 20 or 25 kilometers from the summit of Santa Ana volcano. And there's a natural interest to understand more what should be done in terms of preparedness, and also understanding the overall eruptive history of the volcanic arch. And then, as mentioned, so we're obviously also very interested in research. So to date, there is, I want to say, limited understanding of the underlying plumbing system, except for the obvious observations, right? You have two volcanoes within a few kilometers, one being extremely effusive and the other one more phreatic type eruptions. Why is that? Is there a different source of the magma, different chemistry, or are there other explanations for these different types of eruptions in such a close proximity? Okay, now let's talk about the instruments we used. And as said, the backbone of our network are the Raspberry Shakes. As said, their mission is as well to support mainly education and outreach campaigns. But it turned out we have very good experience in supporting our research goals. So when we jumped in, we obviously knew that people had tested the Raspberry Shakes before, and they had pretty decent results. It's it's a short period instrument, and I want to say it has some sensitivity down to about 2 hertz. But within that limitation, it being more short period, it turned out to be a very good seismic instrument for our application. So right now we have I want to say 7 Raspberry Shakes deployed. We had the Goebels that were donated from Syria. We're working with the Ministry of the Environment, and we're now fully sharing our data with them, and they're sharing their nanometrics data. There are 2 broadbands in the overall area. And then now we're experimenting also with the geobits and DGOS. We have 2 borehole stations and then also 1 surface. So, and the geobits are both seismometer and accelerometer. So we're quite excited about more utilizing these systems more highly in the near future. So one great advantage of the Raspberry Shake system is that each station runs a seedling server on the Raspberry Pi, so data transmission is very straightforward, and so we're able to feed this directly into our SeisCom server and, in essence, analyze and process the data roughly in real time. So I put in a few pictures just to see, we're somewhat creative, maybe a little bit unorthodox. Is that we duct taped a lot of the Raspberry shakes on the ground. That kind of worked out reasonably well for us. We put a little bit of thermal insulation on top and try to keep the worst insects off of the instruments. And this is one of our borehole deployments, just direct burial. And the colleagues at the university in Santa Ana recently also completed the construction of a seismic vault. So this is about, I want to say, 4 meters deep. And so there's plenty of space of deploying different types of instruments now right at the university. This is what the network looks like, and centered around Santa Ana volcano. And then the color coding is for different types of instruments. All of the green ones are the Raspberry shakes, and then different broadbands. And this SA station is one of our geobits. So the network itself kind of unfolded a little bit depending on how we got access. But right now, since we moved a little bit further along in the project, the next goal will be to have 2 concentric rings, in essence, with these instruments, right? So we already have 3 or so that are pretty close to the volcano. We have a little bit of a gap here, but having a bit more dense instrumentation really close will be helpful, right? Just to characterize the processes right associated with Santa Ana and Izalco. But then we also have the more regional deployments that will help us to understand, tectonic processes and faulting, and also construct better regional velocity models. So I believe with these 2 sort of concentric rings, we should be able to accomplish these goals on the scientific front. Okay, so let's look a bit at the first results and our data processing. And again, a lot of student-led work and analysis on this front. My student, Sadia Rinti, she led some of the efforts here with constructing the first seismicity catalog. And, without going into too much detail, we talked about the real-time system with the Raspberry shakes. We set up an automated workflow in SeisCom, but we also review manually, the students, that is, review manually essentially all of the data that comes in. So we start, we improved this, shall we say, the first SeisCom catalog, the analyst catalog, first by refining the 1D velocity model with Velest, including some level of a lower velocity at the surface. And we see Velest is more of minimal refinement, I would say, on the velocity side. But that was step 1, improving 1D velocity model. We relocated with nonlinear, and then we also used waveform cross correlation and GROW-CLUST to have more accurate relative locations. And you can see the improvement on the travel time residuals from the initial SeisCom in red to the Velest, and then to nonlinear in green. Okay, so this is what the catalog looks like, and a few kind of particular aspects of the catalog, are important to point out, right? So there are clear seismically active zones on shore, and there are several of them, and they may not necessarily be related to magmatic or volcanic activity. And so we're trying to separate these processes out. But the first order observation is, we see a clear distinction between the offshore subduction zone events and the onshore, what may be tectonic faulting or magmatically driven seismicity. And it's, you can basically just plot up the frequency magnitude distribution and you'd see this clear shift, right? So we record a lot more smaller events if they're close to our network, but we also record these larger, the subduction zone events if they are larger. So we have these two different distribution of seismicity with a different magnitude of completeness. So this is one, and sorry, let me. And the second component is we also have a interesting change in sensitivity for day and nighttime recordings. And this is maybe one of the biggest challenges that we're facing right now. On the right-hand side, again, frequency magnitude distribution with the completeness maybe up to about 1.4 during the nighttime when the schools are closed. Everything tends to be a bit more quiet, less urban and anthropogenic noise sources. And then during daytime operation, it jumps up to about 2.1. So this is one of the biggest challenges we have. So really not so much instrumentation at this point, but by design, we're working with schools, but expectedly we have pretty high noise because we are in the towns and in the smaller villages, but there are significant noise sources that we have to deal with, right? We had some modest, occasional timing problems, but this is not a significant issue. The other significant problem that we're dealing with is still the loss of power and internet. So the Raspberry Shakes are directly connected to the electricity grid, and we rely on the internet. We basically through Ethernet directly connect to their routers. We had some schools that unfortunately lost their internet connection during holidays. So if the students go home, let's say, November to January for the Christmas break, then the provider shut off the internet. So we're still kind of navigating some of these specific things to our deployment sites. But yeah, so just to give a bit of a flavor of what we were recording. So these are the distal subduction zone events. They're larger events, very nice, clean seismograms, and a larger separation between S and P, and extremely active. We have a ton of these events all the way down from Nicaragua up Guatemala, and so it's very active. And then we have the proximal events, which you can easily spot the difference by just looking at the seismograms. Interestingly enough, we have what we believe to be long period events that are recordable on the Raspberry Shakes. So assuming that long period events are recharacterized by energy 5 Hertz and below, and the Raspberry Shake has some sensitivity out to 2 seconds, we seem to be able to record them fairly well. And at this point, we haven't put a lot of effort in characterize them more and improve locations and such, but this is an interesting, first observation. So in the following, we'll mainly focus on these guys here, the proximal, what we believe to be VTs or just simple or tectonic events related to tectonic faulting. So here's this is a snapshot from our SeisCom, but this is what first catalog looks like, right? And with the network. And one, so right when we started recording, there was a very interesting seismicity swarm. The network started operations in December 23, in essence, when we had, a lot of the stations in place. And then right after Christmas, I think it was the 26th or so of December, or maybe the 28th, this swarm started unfolding, and with major activity in late January of 2024. Okay. This is where the swarm was located, just to orient us, right? So this is again Santa Ana volcano. This is the city of Santa Ana, and this is the El Salvador and Guatemalan border. So we looked at this activity, and I personally got actually quite worried because this was the first sequence I saw that we recorded, and it's rare to see this increase in rate and in magnitudes, well, at least for, for most seismically active areas. At least, it's just so systematic. So my conclusion was, of course, well, if something, is this the precursor to something bigger, right? And we were, communicating with the Ministry of the Environment and obviously also with the university in El Salvador. But I think the graph speaks for itself, right? So this is from November until 2023 until February 2024. So we have these sporadic bursts of seismic activity, and we have the step-like increase in rates associated with these bursts, and the magnitudes seem to be increasing quite systematically until late January, early February. And then the swarm largely turned off. It's sort of still intermittently active, but the activity itself, being located about 12 kilometers from the volcano, we did not see any evidence of processes at the summit that would be any reason to be concerned. Okay, so and in a minute we'll dive a little bit deeper into the statistics of these events, and they seem to be really of tectonic, of fault focused origin. Okay, as opposed to being related to, let's say, a hydrothermal or a magmatic process. Okay, so these are what the seismograms look like. I just wanted to show what the Rossby Shake network recorded, and overall, I would say, pretty clean, nice seismograms. So these were two magnitude 4s that happened very close to each other, and we were able to manually pick and locate them, but also a bunch of activity before and after of smaller magnitude events. Spatially, this is what the sequence looked like before and after relocation. And Santa Ana volcano, so the left-hand side is before relocation, the right-hand side after Grocas relocation. And Santa Ana volcano being located here. And I said it's about 10, 12 kilometers and between 5 to 10 kilometer depth. So not super shallow, but also not extremely deep. So with the relocations, we were able to distinguish two localized clusters, both lateral separation and then also depth separation. Now, obviously, right, we're thinking, what is the underlying process? It looks swarm-like. Is this indication of magma migration or hydrothermal fluid or some other processes, volatiles, or tectonic clusters, as let's say a classic main aftershock on a tectonic fault? And so we looked at the migration and then also at the clustering characteristics. So we'll start with the migration and then we'll look at clustering, space-time clustering with the nearest neighbor approach. Some evidence, for modest migration initially towards the volcano, but then stopping at about 10 or so, 8 or 10 kilometers, and then modest migration again in the opposite direction after the main shock occurred. So this is on the y, right? Distance to the volcano and then time to the largest event, which was about a magnitude 4.2. And the migration within each cluster already started looking fairly main aftershock-like, where everything sort of happens very rapidly and no diffusive lag, so to speak, between subsequent events. Okay, so this is all that what this graph should be showing. But yeah, so we try to dive a little bit deeper using a nearest neighbor clustering approach. And this has now been applied to many different types of seismicity, including predominant tectonic seismicity in Southern California, but also induced seismicity, repeaters, global seismicity catalogs, and now we're using this for the volcanoes. And interesting enough, it looked, so let me back up for a minute, right? So the idea is that you measure the distance in time between offspring and parents. So you define parent events as the event that preceded the offspring, and it's the closest event in space and time. And you're basically normalizing the space-time measurement by the parent magnitude. And the method, without requiring a lot of data fitting or parameter estimation, really allows to separate out independent background events. And this is, on the right-hand side, Southern California, left-hand is Santa Ana. So it separates out the independent background from the clustered events, which could be aftershocks or could be other types of triggering relationships. So one, first order observation, right? It looks very interesting that Santa Ana seems to be dominated by this aftershock mode, right? So to the left, these are events that are very close in time, and down are events that are very close in space. And we do have about 2 modes. So there is a background mode in Santa Ana as well, a bit more localized. It's a smaller study area, but there seems to be a clear separation and the dominance of closely space-time clustered events that look like aftershocks. So we went a little bit more deeper and looked at each event family that was clustered and analyzed the tree topology. And, without going into a whole lot of detail, the idea was if something unfolds more gradually, let's say a fluid-driven swarm, you get this longer generation of triggered events, right? So the first event is causing the second event, the second is causing the third, fourth, fifth. So you have this long chain of events, and then what we call the leaf depth, right? In this topological view would be a large number, average leaf depth. For an aftershock sequence, this topology is very different. You have one main shock that causes a bunch of events that are directly connected, right? So these are offsprings all of the same parent event. And this leads to a leaf depth that is a very small number. So here in this example, it's 1.17. Now for our Santa Ana data set, things looked a lot more burst aftershock-like than swarm. And we're plotting here the average leaf depth as a function of family size. Indeed, for most given clusters, it looks quite a lot more burst-like. And maybe the figure that illustrates it the most is the one on the left, right? So we have one dominant main shock, and a lot of the subsequent events are directly linked or in essence caused, at least statistically speaking, right, are linked to this one main shock. So implications are, okay, this looks more like main aftershock and a tectonic event, and we don't see, the diffusive time lag in the migration. We don't see evidence for the swarm-like topography. So it's hard. It may be unrelated to magmatic or other processes. Now, one other real interesting observation we had, and I'm going to unpack this here over a few slides. And this is, basically the last observation I would like to show is this type of interaction. So I talked about, there were previous observations of kind of far field coupling. We had this 2001 event that happened offshore, and then 1 month after we had the strike slip event. Here we have another instance, right? So we had this event in Guatemala in January 2024, and then we computed a local magnitude of 6.4, a moment magnitude was 6.1, but we saw this rapid increase in rates, very soon after the event happened, right? So this is the seismicity over this time frame in our study area, and you have this step-like increase. So this is too far to have a static impact, or at least too much of it. And so the question is if there is a potential for dynamic triggering. And so my student Adam and I looked at this in more detail and looked at a bunch of additional events we had since. And I think it's fairly convincing to say that dynamic triggering seems to be occurring, and it's quite pretty common around the volcanic area. So this example is from the Honduras 7.6. So actually, it's out in the Caribbean, north of Honduras. It's an offshore event, magnitude 7.6, and we see So this is bandpass between 110 seconds, and then we also have the high-pass waveforms. So very quiet before, and then we have all of these spikes that are happening here. And Adonai looked at computing the energy ratio of blue being after and B before. So basically band passing the waveforms to only get the high frequency energy. And this ratio then is indicative of if there is an increase in high frequency energy radiation after the surface waves pass. I think it's, quite convincing to say that, just from looking at the seismogram and then also doing this more quantitative analysis, that there was pretty widespread dynamic triggering related to this event. And we're looking at a few additional ones, such as the Kamchatka event, the 8.8, about, a couple of months ago, which also seemed to have at least modest dynamic triggering in our study area. Adonai is also working on refining the catalog now using machine learning, and he has some really good first results. And we're able to extend our analyst catalog, record more small magnitude events, which may be very instrumental in understanding the potential dynamic triggering relationships, right? So we're looking for rate changes, and they're most robustly measured using small events. So obviously having a more complete catalog will be very instrumental, right? And this is a first preliminary catalog. It was generated with machine learning, and we're still refining the magnitude to provide, now we're using, at this point in time, we're using two different methods to compute the local magnitudes. So this is why we have some discrepancy here between the machine learning and the analyst catalog. Okay, so let me summarize some key points, right? And I realized I covered a lot of ground from how the project unfolded and the training and education and such. But I just want to make 3 points, and then happy obviously also to answer any questions. But want to highlight, so we have very positive experience with working with Raspberry Shakes, both in terms of their instruments and them as a company. Very supportive and has been perfect for what we're doing. I hope we'll see what the long-term lifetime of a Raspberry Shake is. Hopefully 10-20 years. We'll find out. We'll report back. But so far we reliable and re-approved great for training, education, and for the science, right? I do want to emphasize these are very useful short period seismographs that help for doing, local monitoring and seismicity catalog creation. Now, I think we're sort of on the, we're starting to see that the seismicity clustering is very useful, especially in places like El Salvador, where everything happens together, right? So you have volcanic, magmatic, you have the subduction zone, and then you have some tectonically active faults. And we do want to separate these different types of seismicity out so we can understand what the underlying processes are. I would say the nearest neighbor approach is useful to do that. And the sequence that I showed in this talk was mainly burst type and related to tectonic faulting, most likely. And this new observation, right, that Adonai highlighted is that Santa Ana, the volcanic area, seems to be quite sensitive to dynamic triggering. So far, we're only collecting the observations, but then the implications, right? We'll obviously want to ask why. What is this indicative of a stress state or of some other processes, presence of fluids, pressurized fluids in faults and cracks? So this will be the next step in this part of the project. Okay, some of the results can be seen in our SIL paper from earlier this year. And well, thank you for your attention. I'm happy to answer any questions.